Liquid green hydrogen. It's not just a futuristic concept, it's one of the most promising answers to one of the toughest energy problems of our time: how to store and transport clean hydrogen across long distances, efficiently, and at scale. Green hydrogen, made by splitting water using renewable electricity, is already a star player in the clean energy race. But storing it as a gas, even at 700 bar, means low density and huge logistical challenges. So what if we cool it down? All the way to minus 253 degrees Celsius. At that cryogenic temperature, hydrogen becomes a liquid. It shrinks dramatically in volume, about 800 times more dense than its gaseous form, making it easier to store, ship, and scale. But liquefying hydrogen isn't easy. It starts like any green hydrogen process: electrolysis. Water is split using solar or wind-powered electricity, with technologies like alkaline or PEM electrolyzers. Then comes purification, removing any water vapor or oxygen because even the slightest impurity can freeze during cooling and block the system. Next, the hydrogen is pre-cooled, often using liquid nitrogen, before entering the heart of the process, the cryogenic liquefaction stage. This uses a combination of heat exchangers, compressors, and expanders working in a sophisticated thermodynamic dance, transforming hydrogen gas into a dense, frigid liquid. One key challenge here is ortho-para conversion. At room temperature, hydrogen exists mostly in one molecular spin state, but at cryogenic temps, it must shift to another state. That conversion releases heat, and if it happens too late, it can cause unwanted boil-off. So catalysts are used to speed this up during the cooling process. Once liquefied, hydrogen is stored in vacuum-insulated tanks with ultra-thin reflective layers, minimizing heat ingress. But even then, a small amount boils off every day. Managing this is part of the complex logistics of handling LGH2. So where does this super-cold fuel make sense? Think long-haul aviation. Airbus and others are developing liquid hydrogen aircraft, or maritime shipping, where energy density is everything. LGH2 is also being eyed for intercontinental hydrogen trade, linking renewable-rich regions like Australia to energy-hungry nations like Japan and Germany. It's also vital for industries like steel, ammonia, and high-temperature processes, where gaseous hydrogen might fall short. But this isn't a silver bullet. Liquefying hydrogen consumes up to 35% of its energy content. The equipment is expensive. Materials must withstand extreme cold and hydrogen embrittlement. And safety? A top priority. Hydrogen is flammable, and handling it as a liquid requires specialized knowledge and infrastructure. Still, the benefits are hard to ignore: high purity, high density, and the ability to move clean energy across oceans. The future of liquid green hydrogen depends on innovation. Better refrigeration cycles, cheaper catalysts, smarter insulation, and global infrastructure rollout. The race is on to chill hydrogen affordably, safely, and at scale. Thanks for watching. If you enjoyed this deep dive, don't forget to like, subscribe, and hit the bell icon. This is MixMind 7090, exploring the tech that powers tomorrow.